Hello everyone, and welcome back to our third video in Chapter 2. This video is going to be extremely important, and I anticipate a fairly extensive discussion, so you might want to go grab a beverage and pop you some popcorn, because we are about to start discussing the properties of water, which is going to be far and away one of the most important molecules that we discuss this semester, and the importance of water cannot be understated, and it's going to show up again and again and again throughout every chapter that we go through. So we talked a little bit about water as kind of a shining example of a polar molecule, and we discussed a little bit about what that polarity means, in the sense that your oxygen atom has an unequal sharing of electron with the two hydrogen atoms that it gets into business with. So usually the way that molecules operate is that when they kind of figure out their molecular geometry, molecules are usually going to try to position their covalent bonds in three-dimensional space so that the surrounding atoms get about as far away from each other as they possibly can. Now, if you just look at water here, you can see that that doesn't really appear to be the case, right? So you've got a hydrogen atom over here and a hydrogen atom over here. They look like they're kind of close together. It seems like water could do a better job of getting those hydrogen atoms further apart from one another. So for water, you would think that the molecular geometry would be that your bond angles would be 180 degrees, which is what you would see for a kind of similar molecule like carbon dioxide, something that also contains a total of 3 atoms. Well, the major difference with water is that because of oxygen's unusually high electronegativity, this oxygen atom actually has 2 pairs of unshared electrons that also take up space in the geometric sphere that we're talking about. So we can't get these hydrogen atoms to be 180 degrees because then they'd start clashing with these unpaired electrons. They would repel each other. So for water actually ends, and I'm having kind of the same issue with my slides that I had before, but I'll go ahead and kind of tell you what would be popping up down here. The way water actually works is that we have a bond angle of 104.5 degrees, so that ends up being the perfect geometric bond angles for keeping these hydrogen atoms as far apart from each other as they can possibly be, and also as far apart from those 2 unpaired pairs of electrons, which look like they're imaginary, but they actually take up some geometric space here. So this ultimately ends up meaning that water, geometrically speaking, is a bent molecule, and that's a big reason for water having its polar properties, meaning that you have the partial negatives on this side and the partial positives on this side. So let's compare that real quick to carbon dioxide. So carbon dioxide and water actually make a pretty decent basis for comparison because each molecule contains 3 atoms. We talked a little bit about this before, but if you're talking about carbon dioxide, which you can see down here, if you compare the electronegativity of carbon and oxygen, we obviously saw before, oxygen has a much higher electronegativity. So carbon dioxide is constructed by using 2 polar covalent bonds. In spite of that, carbon dioxide is a non-polar molecule. And our explanation for that is that because the bond angles for carbon dioxide literally are 180 degrees, the polarity going this way is canceled out by the polarity going this way. So even though each individual bond is polar covalent, the 2 polar covalent bonds pointing in opposite directions cancel each other out, so the whole molecule is actually nonpolar. If you compare that back to water itself, because of water's bent geometry, there is no canceling each other out because you don't have 2 things pointing in exactly opposite directions. Those things I reference are in chemistry terms called dipoles. The 2 dipoles are not pointing in opposite directions. So there actually is some summation here, and all the negative charges end up around the oxygen atom, and then the lack of negative charges, meaning the partial positives, end up around the hydrogen atoms. So that's our explanation for why carbon dioxide is nonpolar, but water is polar. Water is bent and has those two non-paired pairs of electrons, whereas carbon dioxide is linear, has 180-degree bond angles, and does not have those unpaired electrons. So what we'll see here is that water, if it behaved like methane, which is CH4, where methane actually is a tetrahedron, then water would have a bond angle of 109.5 degrees. So water, even though it looks more like carbon dioxide in the sense that it only has 3 total atoms, water actually behaves a lot more like a molecule that has 5 atoms, like methane. So the bond angles between water and methane are a lot closer than the bond angles between carbon dioxide and water. Okay, so let's start talking about hydrogen bonding. So when you have polar molecules like water, and water, of course, is not the only polar molecule out there, so ammonia, NH3, is another good example of a polar molecule. But when you have polar molecules that have weakly positive hydrogen atoms, like we see that water does, these molecules become capable of a very special type of chemical bond that we have not talked about before. We've talked about ionic bonds, and we've talked about covalent bonds. Well, this is called a hydrogen bond. The hydrogen bond is the result of electrical attraction in very much the same way that the ionic bond was the result of electrical attraction. The difference is that ionic bonding is actually fairly strong because you have an attraction between a full positive charge and a full negative charge. Hydrogen bonding is going to be quite a bit weaker. So this is the result of attraction between a weak positive and a weak negative, a partial positive and a partial negative. So this is the result of polar molecules attracting each other. So if you look at water forming hydrogen bonds here, you have the weakly positive hydrogen ion electrically attracted to the weakly negative oxygen atom of a different water molecule. So hydrogen bonding is not bonding within a single molecule. Hydrogen bonding is an attractive force between at least 2 different molecules at the same time, what we call intermolecular forces. So if you find it helpful, you can think of a hydrogen bond as being like an especially weak ionic bond. It's still the result of electrical attraction between positives and negatives. It's just in this case, the hydrogen bond is actually fairly weak because you're dealing with partial positives and partial negatives, not full positives and full negatives. So you might see that and think that, okay, well, how important can hydrogen bonding actually be if a single hydrogen bond is very weak? Okay, yes, it is true that a single hydrogen bond is much weaker when you compare it to a single covalent bond or a single ionic bond. That does not mean, however, that hydrogen bonding is insignificant. It's actually very, very significant because you're not likely to ever see one hydrogen bond at a time. More than likely, you're going to see many, many, many hydrogen bonds all forming simultaneously, and they become part of an extensive and vast network of hydrogen bonds. If you look at this lake here, obviously you've got many, 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 many millions of gallons of water here. Well, if you consider the molecular structure of that water, all the water molecules that are in that liquid are hydrogen bound to one another. So you have a very vast geometric network of hydrogen bonds that are all holding the water molecules together. As we're going to see when we start discussing the properties of water, this vast network of hydrogen bonding is the biggest reason why water is a liquid at room temperature. So, because these hydrogen bonds between all the different water molecules in this network, because all the strengths of those individual hydrogen bonds, and remember, a single hydrogen bond is very weak, but when you add up all of these hydrogen bond strengths together, because they're all there at the same time, collectively, hydrogen bonds actually have a very vast amount of strength. For example, if you wanted to boil all of the water in this lake and vaporize it, you would have to break every single hydrogen bond that exists between every single water molecule in the lake. That's a lot of energy that you would have to be providing. Okay, so let's start talking about the properties of water. And what I want you to kind of keep in mind as we start discussing these is that all of these properties in some way relate to water's polarity and its ability to form hydrogen bonding. There is a connection there for every property of water that we are about to discuss. The first thing that we should discuss, and this is something that is actually going to be fairly common to all of water's properties, is that water molecules tend to cling to each other because of that hydrogen bonding. You're not going to get two water molecules together and have them not hydrogen bond to each other. So water molecules tend to stick to each other fairly well. So, like I said, a lot of these different properties of water that we're going to talk about that are unique to water are because of the hydrogen bonding, and it actually makes water such that it is an ideal biological solvent. Any liquid-based media you see in biology, whether it is bodily fluids, cellular fluids, or whatever, water is the solvent, and water is the basis for all the properties of that living cellular material. The first property that we will discuss, maybe not the most exciting one, but water has a high heat capacity. Okay, now what in the world does that mean? Well, heat capacity in chemistry terms is defined by the amount of thermal energy it takes to heat a substance up by 1 degree Celsius. So if you have a beaker full of water and that water is at 20 degrees Celsius, the heat capacity refers to how much heat are you going to have to add in order to heat that water up by 1 degree. Okay, so what we're saying here is that water, when you compare it to similar substances that have kind of similar atomic makeup, water has an unusually high heat capacity. It takes an unusually high amount of heat to raise or lower the temperature of water. So this becomes significant. Essentially what we're saying here is that the temperature of water rises and falls slowly and gradually. So you're not going to get water heating or cooling extremely quickly. It's going to be kind of a slow and gradual process. So from a biology perspective, this is important because it's going to allow organisms kind of an easy way to maintain their normal internal temperatures, considering that most organisms are, a majority of their molecular structure is water, so that will help to protect these organisms from rapid temperature changes due to changes in the environment. On a similar note, our next property of water is that water has a high heat of vaporization. So the idea here is that, like I said before, if you want to evaporate water, meaning you take it from a liquid phase to a gaseous phase, you're going to have to break all of the hydrogen bonds in the network, and that's going to require a lot of thermal energy. So in this case, we're not just talking about water's heat capacity, we're not just talking about raising the temperature of water, we're talking about completely changing its molecular phase. So we take advantage of this for us warm-blooded organisms. We take advantage of the fact that it does require so much heat to vaporize water because this is how sweating works. This is how we keep ourselves cool when it's very hot outside. So basically, we rid our bodies of excess heat by secreting water onto the surface of our skin, and then that excess heat is used to vaporize the water. So that heat basically dissipates, and in the process, we vaporize the water right off the surface of the skin. So I will have a figure on the next slide to kind of illustrate that point further. But before we get there, let's go ahead and introduce the third property of water, which is that water is a good solvent. And I've mentioned this several times before. A solvent is just a liquid that can dissolve individual solute molecules to form a solution. So a solution is the most important type of liquid mixture that we're going to encounter this semester. A solution, in biological terms, is going to consist of water and then all the stuff that is dissolved in water. Your blood plasma, more specifically, is an example of a complex biological solution. Your blood, even though you might not think of it this way, your blood plasma is just water with a whole bunch of stuff dissolved in it. Salts, sugars, biomolecules, and things like that. So again, the reason for all of this is water's polarity and its inclination to form hydrogen bonds. So because water is very polar, It makes for a really good solvent because, as we're going to find out in the next chapter, a lot of really important biologically relevant solutes are also polar. So if you've never heard this expression before, like dissolves like, water as a polar solvent is going to want to dissolve polar solutes. You're not usually going to have much success dissolving a nonpolar solute in a polar solvent. Think of what happens when you try to get oil, which is nonpolar, to mix with water, which is polar. Okay, so here's what I mentioned before with water's high heat of vaporization. Kind of the less steep portions of the curve, like what you see right here. This is what we were talking about when we said that water has a high heat capacity, meaning that it's going to take a lot of energy to get the temperature of water to increase. So kind of the more flat parts of the curve here are referring to water's high heat capacity. The really steep parts of the curve here is what we're talking about when we say water has a high heat of vaporization. You'll notice you get to the point once you get water to reach 100 degrees Celsius where you have to put in a certain amount of thermal energy before you can increase the temperature anymore. And at that point, you change phase from liquid to gas. So in the kitchen, when you boil a pot of water, you're increasing the temperature of water from room temperature all the way up to 100 degrees Celsius or 212 degrees Fahrenheit. Once you get the water to that boiling point, water is not going to boil right away. That water is not going to vaporize because this 540 calories of heat that is indicated here, that is the amount of thermal energy that is necessary in order to break all of those hydrogen bonds. Okay, so before we get to the next property of water, let's have kind of a sidebar here and talk about something that's very important. Whether or not a molecule is going to dissolve in water. This is a very important question, not only in general biology, but more specific fields like physiology and immunology. So we're going to introduce two new terms here. The first term is called hydrophilic. So if a solute, meaning a molecule that has the potential to dissolve in a solvent, if a solute is hydrophilic, that means that it really likes water. The hydro part of that refers to the water itself, and the philic refers to having a like for something, having an affinity for something. If you are a bibliophile, you really like books and reading. If you're an audiophile, you really like sound and listening to music. So if a solute, if a molecule is hydrophilic, it really likes water. It really wants to interact with water. So hydrophilic solutes are going to be those that are soluble in water. They can dissolve in water. And usually the reason for this is that these solutes are polar themselves. They're very similar to water, or they are ionic compounds that can break apart in water. So this is what I meant when I said like dissolves like. Water is polar, and most hydrophilic solutes are going to be polar as well. So some good examples of hydrophilic solutes are salts, which are ionic compounds, so we've covered that before. Sugars, which are very polar molecules. Alcohols, which tend to have some polar properties. And then acids and bases, which have some properties that are going to resemble salts as well. On the other hand, if a solute is hydrophobic, it is not going to be soluble in water because the word hydrophobic literally means a fear of water, okay? So hydrophobic solutes are going to tend to be very nonpolar and have no electrical charges that water molecules can interact with. So, excuse me, so again, this all ties back to water's polarity and its inclination to form hydrogen bonds. If water is going to dissolve something, water has to be able to interact with that molecule. It has to have something to grab onto. Water can interact with all of the hydrophilic solutes here because they either have fully positive or negative charges that water can grab onto, or partial positives or partial negatives. So through the hydrogen bonding process, water is going to use its partial positives or partial negatives to attract itself to the partial positives, partial negatives, or full positives or full negatives of the hydrophilic solutes. Hydrophobic solutes do not have anything that water can grab onto in that regard. It would be like trying to open a chest of drawers that has no handles. You got nothing to grab onto, so you're not going to be able to get a good purchase on it in order to open the drawers. So because hydrophobic solutes have nothing for water to grab onto because they are very nonpolar and they don't have any electrical charges on them, water can't grab onto them and water cannot dissolve them. So some good examples of hydrophobic solutes are molecular gases like oxygen and carbon dioxide and nitrogen, which are not very soluble in water. Fats and oils, you probably know what happens when you try to get water and oil to mix. They don't mix and they form two different layers. And then a type of molecule that we will talk about in the next video called hydrocarbons. So if you look at this figure here, you can actually see everything that we just discussed in action. Water molecules become attracted to each other through hydrogen bonding, as we discussed before. Well, the same is true when you talk about water attempting to dissolve another molecule. In this case, we've got this organic molecule that has a polar component to it. So you can see this big organic molecule here has a big oxygen-hydrogen group here, and because that is a polar group, it gives water something to grab onto. So this molecule would be fairly soluble in water. It has some hydrophilic properties. But when you talk about something like oil, which is just going to be a whole bunch of non-polar carbon and hydrogen bonds, water has nothing to grab onto. So if you do try to get oil and water to mix, they are not going to mix and they are going to form two different layers, with water being on the bottom because it is more dense than the oil on top. So oil in this regard, because it is so nonpolar, it is hydrophobic and it really doesn't want to have anything to do with that water. Now, if you consider something like a sugar molecule, which you can see here, this sugar molecule has a whole bunch of polar OH groups surrounding it. We call those OH groups hydroxyl groups, and we will more aptly define those in the next video. Because the sugar molecule has a whole bunch of these OH groups that are polar, water has something to grab onto, and water is going to do a very good job of dissolving sugar, because sugar is a hydrophilic compound. And then in the case of ionic compounds like salts, we've already seen that sodium and chloride will separate from each other or dissociate when you put it into water. So water basically shields the fully positive or fully negative charges and completely dissolves the salt into the water. Okay, so with that sidebar out of the way, let's talk about the other properties of water. Number 4, water molecules are both cohesive and adhesive. So if those two adjectives sound very similar to each other, it's because they are very similar to each other, but they are two different definitions that we're going to have to kind of distinguish from each other. So when water acts as a cohesive, that means that water molecules are clinging to each other, which is something that we're already familiar with. And we know this is the case because water molecules hydrogen bond to one another. So water molecules are cohesive because of hydrogen bonding. Well, water is also adhesive, and in this regard, it means that water molecules also will cling to surfaces if those surfaces have polar properties. So water molecules will not only cling to each other, but they will cling to flat surfaces if those surfaces are polar. So in both cases, this is because of hydrogen bonding. So this actually brings up some important points. The cohesive properties of water will account for a body of water or the ocean holding something called surface tension, and it also accounts for water's ability to flow freely. We will address surface tension on the next slide because I've got a good picture that illustrates that pretty well. The adhesive properties of water are going to account for water's ability to be transported through narrow vessels, and this phenomenon is called capillary action, and I will have another slide dedicated to that here in just a second. So for the surface tension of water, you can see that this little pond skimmer here, which is a little insect, a very lightweight insect, is able to stand on the water without sinking to the bottom or even really exposing itself to the water at all. You can see that the pond skimmer's legs make indentations in the water But the surface of water is not broken because the amount of force the pond skimmer is placing on the surface of the water is not sufficient to break the hydrogen bonding at the water's surface. So this is what we refer to as the surface tension of water. There is because of the hydrogen bonding properties that cause the cohesive water molecules to cling to each other, you're going to have to provide more force than this pond skimmer is in order to break the surface of the water and break those hydrogen bonds. Now, in the case of capillary action, this is describing this phenomenon where if you place a narrow tube into water, the water will start climbing up through the tube because the water molecules are going to start clinging to the inside surface of this tube. And as the water molecules reach kind of the top part of the tube, water molecules, a small percentage of water molecules, start evaporating, and they kind of start pulling the liquid surface of the water up with them. The capillary action phenomenon gets more and more significant the narrower the tube becomes. You can see this kind of wider tube doesn't get as much capillary action going on, whereas the very narrow tube does a much better job of it. The best example of capillary action in biological systems is what you see in plants and their ability to draw water up to their leaves through the roots that are exposed into the bottom of the ground. So in this tree that you're looking at here, the challenge we can identify right away is the source of water the tree is drawing on is down here in the ground itself. So we need to pull the water up through the roots and transport that water up to where the leaves are. Now, it doesn't take much imagination to kind of figure out what the challenge there is. You're trying to transport water up against the force of gravity. Well, this is where capillary action comes into play. We draw water up because water has those adhesive properties that we talked about previously, which are due to hydrogen bonding. Water is able to move up against the force of gravity by adhering to the sides of very narrow vessels within the root and within the trunk of the tree itself. And because of this capillary action, the evaporation of water pulling water up against the force of gravity, we are eventually able to get water delivered up to the soft green leafy tissue of the tree itself, which is the portion of the tree that needs the water the most. Okay, our next property of water is that frozen water, which is ice, that's solid water, is actually less dense than liquid water. Now, this is a surprise if you've never heard this before. So typically when you talk about density, so density is mass per unit volume, you would expect a solid to be more dense than a liquid. That's true in almost every case, but not for water. Water is unique. Number one, water, based on its molecular weight of about 18 AMUs, based on water weighing about 18 AMUs, the 16 from the oxygen and 2 from the 2 hydrogens, based on water having a molecular weight of 18, you would expect water to be a gas. So carbon dioxide is actually heavier than water, and carbon dioxide is a gas. Water is lighter than carbon dioxide, but it's a liquid. So it's like, how does that work? Well, again, it's all because of the polar hydrogen bonding properties of water. So this is how we can explain solid water, which is ice, being less dense than liquid water. So the way we can explain this is that in ice, each water molecule is going to form about 4 hydrogen bonds. So whichever water molecules it can get its hands on, a single water molecule will form a total of 4 hydrogen bonds with the water molecules that surround it. In liquid water, this is only about 3 hydrogen bonds. So water molecules in ice are a lot more open and expansive and a lot less dense. So again, the hydrogen bonding ability of water is your explanation for all of these properties that we've discussed, including the idea that ice is less dense than water. But why is that important? Well, just look at this picture here and you can see why it's important. You've got this family of sea lions that are living on a block of ice, and the whole reason that ice is floating on the water is because the ice is less dense than the water. That's why ice floats. It's because it is less dense than the liquid water. So the idea here is that if the ice were more dense than the water, like we would usually tend to expect, the ice would all sink. And if all the frozen water sinks down to the bottom, you're going to have even more water at the top freezing and sinking down, freezing and sinking down. And this is going to lead to a situation where entire bodies of water completely freeze over. And that would be very, 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 very bad for all the aquatic organisms that are living down at the bottom. But because ice is less dense than water, the water on top of the body of water freezes and stays on top, and that acts as an insulator and prevents the water deeper down from freezing, and it preserves the ability of aquatic organisms deeper down to be able to continue living and operating. So this picture kind of shows the same thing. You've got the top of this pond that is frozen over, but the water deeper in is actually still above the freezing point, and all the different aquatic organisms that are down here are still able to live and operate as best as they possibly can. Okay, so that is going to do it for our discussion on the properties of water, but I actually do have one or two more things that I want to discuss with you about water in particular. So water itself can dissociate into ions. So we talked before about how salts dissociate into ions when you put them into water. Well, it turns out water can actually do this itself, and it does so according to this equation that you see here. A single water molecule can break up into what we call a hydrogen ion and a hydroxide ion. So you can see that we have an H here and then an OH here, and that together makes up all the components of water. But the good news is that water only does this very rarely. So the concentration of these hydrogen ions and hydroxide ions in a pure sample of water is going to be 1 × 10 to the -7th molar, which it basically means moles per liter. So really, a single a sample of water molecules are really only going to do this very, very infrequently. So you don't have to worry about an entire sample of water dissociating all at once. So the reason why we bring this up is because this acts as an introduction to our understanding of acids and bases. So acids and bases are substances that when you add them to water, they change these concentrations. So an acid is a substance that when you add it to water, it causes the hydrogen ion concentration to increase. So normally in a sample of pure water, you have an equal amount of hydrogen and hydroxide, and they are both 1 × 10 to the -7th molar. But if you add an acid to water, you are increasing the concentration of hydrogen ion and decreasing the concentration of hydroxide. And then the opposite is true for a base. This is a substance that when you add it to water, it causes the hydrogen ion concentration to decrease and the hydroxide ion concentration to increase. So in adding an acid or a base to water, you are not only adding a solute to the water, but you're also changing the acid-base balance in the water itself. So we have this convenient scale that we use to measure how acidic or how basic a solution is, and this is called the pH. pH is just a measure of hydrogen ion concentration in an aqueous solution, or a water-based solution. The mathematics here is that the pH is equal to the negative log base 10 of the hydrogen ion concentration in moles per liter. The mathematical lingo here is that the p, the little lowercase p here, literally means negative log base 10 of. So pH means negative log base 10 of the H concentration. Now, generally speaking, in biological systems, this scale runs from 0 to 14, even though mathematically it is possible to go below 0 or above 14, but we'll just stick to a 0 to 14 scale to make things nice and simple. You can actually see here some examples of common everyday things and what their pHs tend to be. Now, the most important thing I want you to understand about the pH scale is that because it is logarithmic, a difference of 1 pH unit is actually a very big difference. Notably, because this is log base 10, a difference of 1 unit means a 10-fold difference in hydrogen ion concentration. Let's look at some examples so we can make sure you get the idea there. Let's do some comparisons. Number one, let's look at blood, which has a pH of 7.4, and compare that to the pH of urine, which we'll say has a pH of 6.4. So blood, 7.4, urine, pH of 6.4. That is a difference of one single pH unit, which means that blood is 10 times more basic than urine. The idea with the numbers here is that the smaller the numbers are, the more acidic things are, and the higher the hydrogen ion concentration is. And the higher the numbers get, the more basic the solution is, and the less concentrated the hydrogen ions are. So blood, being the higher number, is more basic than urine, which has the lower number. And because there's a 1 unit difference, the blood is 10 times more basic than the urine. Or you could flip that around and say the urine is 10 times more acidic than the blood. Let's do another one. Let's compare coffee, which has a pH of about 5, to pure water, which has a pH of 7. So that's something that I didn't mention before. 7 on the pH scale is perfectly neutral, and that is pure water. So pure water has a pH of 7.0. So if coffee has a pH of 5 and water has a pH of 7, that is a difference of 2 pH units, so that means a 100-fold difference in hydrogen ion concentration. So coffee, we could say, is 100 times more acidic than pure water. So every time you have another pH unit difference, you have another 10-fold difference in hydrogen ion concentration. So if we do one more, black coffee, which has a pH of 5, if we compare that to seawater, which has a pH of 8, that is a 3-unit difference, and we would say coffee is 1,000 times more acidic than the seawater. So the thing you should keep in mind about this is that all fluids in biology, whether they're bodily fluids, cellular fluids, or what have you, all biological fluids are aqueous in nature. So they are all going to have an associated pH value that you need to be aware of. So one of the most important things, I'm not going to belabor it for right now, but it's actually very important in biological systems, especially for cellular systems, that the pH does not change too much. So that has to do with homeostasis, which we talked about in Chapter 1. It's really important that your bodily fluids and your cellular fluids do not change their pH values too much. So the natural defense mechanism against changes in pH in biology are what we call buffers. So a buffer is just a mixture of chemicals that is meant to resist big changes in pH. So usually most buffers consist of what is called a weak acid and its conjugate base. In this particular case, which is one of the most common buffering systems we find in the human body, this is the carbonic acid bicarbonate buffer system. Carbonic acid is the weak acid here. It's a weak acid in the sense that it does not really give up its hydrogen ion all that easily. And then bicarbonate, this is what is left over of the carbonic acid after it has lost one of its hydrogen ions, as you can see right here. So the carbonic acid, the weak acid, is in equilibrium with bicarbonate, which is its conjugate base. So this is going to be the nature of how we can resist any changes in pH here. So if we have a chemical reaction that produces a whole bunch of hydroxide ions, which would increase the pH by a whole lot, instead of increasing the pH, those hydroxide ions can just react with any extra hydrogen ions here to make a water molecule so that we kind of nullify the contribution from that hydroxide ion. And then in the opposite regard, if a chemical reaction is going to start making things more acidic by producing a whole bunch of hydrogen ions, that hydrogen ion can react with the conjugate base here to reform and reconstitute the weak acid. So in doing so, on both sides, on the acid side and on the base side, we can buffer the system by preventing big changes in pH from happening by absorbing the effects, okay? So usually what you're going to see is that a buffer system is a little bit limited. It doesn't have unlimited powers, Buffers are usually effective at maintaining a steady pH, but only within a very narrow range. So in this particular case, you can see this buffering range here is indicated as ranging from about 4 to a little bit greater than 6. So if the pH of this fluid is at 5, then we can absorb a certain amount of hydroxide ions up until a point, and we can absorb a certain amount of hydrogen ions up until a point. But once you get beyond that point, the buffer essentially stops working, because if you add too much acid or too much base, you exhaust the buffer and it becomes no longer effective. In other words, if you use up all the conjugate base or you use up all of the weak acid, then you can't really absorb any more hits in that regard. Okay, so that is going to do it on our discussion of water. It was kind of a long discussion, so I thank you for sticking with me here. Join us for one more video in this chapter, and we will start a brief discussion on the chemistry of carbon, organic chemistry, which is going to form the basis for future discussions in Chapter 3 on the nature of biomolecules like proteins and nucleic acids and carbohydrates. Thanks again, and I will see you next time. So long.